So the stuff we're going over today has to do a lot with the lab we're going to be doing on Tuesday. Okay, what we have to know here today, or what we have to get out of today, are some of the properties that ionic compounds show, some of the properties that molecular compounds show, because on Tuesday, you will be given 12 unknown materials. Okay, they'll just be in beakers labeled A through K. That's it. Okay, and you will have to use their various physical properties in order to figure out what their identities are. Okay, obviously one of the first things you'll want to be able to do when you're dealing with these or identifying them is decide which ones are ionic and which ones are molecular. Okay, at least then you break it up into two groups, and then you can start breaking it down from there. But what that's what we're going to go over today is what are some of the things I can look for that can help me to identify this unknown substance. Okay, so there'll be lots of things you'll probably want to highlight or make little notes of that will be useful when you're trying to analyze your results from Tuesday to identify your unknown substances. Okay, so we got to learn the properties of compounds, acids, bases, ionic, molecular, okay, and we've got to understand how those properties can be used to identify them, which, as we said, is going to be useful in our lab design. Okay, so big thing here is that all matter has certain properties. Those properties are either physical properties or chemical properties, right? And all we're going to be focusing on today are the physical properties. Okay, the difference is physical properties you can observe without basically anything else. Okay, a chemical property I will not know about until there's a reaction going on. Chemical properties are things like reactivity, okay, and stuff like that that really I won't know until it happens. I can't look at a material and go, I'll bet that's highly reactive. There's no way to really know that by looking at it. Okay, I mean, you wouldn't know that sodium would explode when you threw it in water just by looking at it. Well, maybe you would because it's usually stored in kerosene. But really, I mean, it's just a soft silvery metal. It doesn't look harmful. It doesn't look dangerous. Okay, but if you throw it in water, it blows up. Okay, so it's kind of a weird thing that way, but it's not something you can tell just by looking at it. All right, so big thing here is we're going to be focused on just the physical properties. Physical properties are things like color, density, melting point, boiling point, solubility, ability to conduct electricity, whether they're magnetic or not. Okay, all of those kind of things are physical properties, okay, that can be determined without being in a reaction with something else. Okay, questions so far? All right, so kind of relating to this would be the difference between a physical change and a chemical change. Can you guys talk about that last year in Science 9? Okay, so if I crumple up a piece of paper, physical or chemical change? Right, it's physical change, still paper. I can still get the flat paper back if I work hard enough. Okay, if I set the paper on fire, that's a chemical change. I'm not getting the paper back after that. All right, it's going to turn into carbon dioxide and water vapor and ash and whatever else. Okay, it'll be a chemical change. After the paper burns, I will have very different materials than I started with. Okay, and I won't be able to get it back. All right, so things about ionic compounds. First off, all, without exception, all ionic compounds are crystalline solids at room temperature. Okay, so that's one big thing, because I mean, the first set of tests we're going to run on Tuesday is just going to be an observable properties test. I'm looking at this stuff. Okay, what can I tell just by looking at it? Okay, well, one of the things we can tell is if it's a crystalline solid or not. Okay, so it's a pretty good bet that if I have an unknown material that's a crystalline solid, it's probably ionic. Probably. Okay, so here's the thing. All ionic compounds are crystalline solids at room temperature. Is the reverse true? No. Okay, the reverse is not true. A prime example could be sugar. Sugar is a crystalline solid at room temperature, but it's a molecular compound, not an ionic one. Okay, so all ionic compounds are crystalline solids at room temperature, but not all crystalline solids at room temperature are ionic compounds. Okay, but is it a pretty good bet? Yeah, it's a pretty good bet. Okay, so that's a big one. Okay, they typically have very high melting points. That would be something if we were actually running a melting point test, which we're not, you'd be able to tell sugar wasn't an ionic compound pretty quickly because it melts pretty fast. Okay, whereas if you were performing the same test on salt, salt would go up to several hundred degrees before it melted. Okay, ionic compounds will conduct electricity when they are in solution. This is your defining test. Okay? This will always tell you if something is ionic or molecular. Okay? So on Tuesday, if we've got a bunch of crystalline solids and we're going to say they're probably all ionic, after we do a conductivity test on their solution, we'll know which ones are definitely ionic. All right, everybody follow there? Now, we got to think back to this. We talked about this a little while ago when we were talking about ionic compounds, when we were first talking about naming, and we said that when they go into solution, that is when they dissolve, they split up. Okay, remember they got what they wanted and they split apart. Okay, well, that's why their solutions conduct electricity. A solution that contains salt, okay, so if I have salt water, is going to contain some sodium and some chlorine ions, negatively charged chlorine, positively charged sodium. That enables electrons to pass between particles and actually flow through the solution. Okay, now, does water conduct electricity? Okay, does distilled water conduct electricity? No. Okay, tap water will, because tap water's got ions dissolved in it. Okay, we put fluoride in the water to keep our teeth healthy. There's calcium, lots of it in our water. Okay, things like that. There's lots of ions and things like that dissolved in tap water, so tap water dissolves electricity. Pool water definitely conducts electricity. Okay, it is the fairly concentrated ionic solution. That's what keeps stuff from growing in it, you know, when accidents happen in the pool. Okay, that's why we have to put all that stuff in there, because it keeps stuff from growing. It's definitely a concentrated solution. It smells a little bit like bleach. Okay, ever notice that the pool smells a little bit like bleach? Okay, because, well, it's chlorine bleach. Really, it's just a weaker solution that's safe for your skin. Okay, so yeah, it's definitely a solution with stuff dissolved in it, so it would conduct electricity as well. All right, so there's two big things that would help us identify ionic compounds. This is a crystalline solid, and then we'll run a conductivity test on its solution. That's the key. Okay, I don't just want to take the powder and go and stick, you know, a conductivity tester in the powder. That's not going to do anything. The solid isn't going to conduct anything, but the solution of it will. So I add water, I can check its conductivity. Okay. There are lots of ionic compounds that produce solutions that are brightly colored. Okay? And it's not by accident. Usually those ionic compounds, the salts themselves, are brightly colored. Okay, so for example, any ionic compound containing copper is blue. Okay, the salt is, like the crystalline solid is blue, and when you dissolve the crystalline solid in water, the solution turns blue, surprisingly. What's that? Well, copper metal is orange, but copper-containing compounds are blue. If you leave copper long enough and it starts to oxidize, the material that builds up on it is kind of a bluish color. Okay, yeah, or greenish, but it's bluish green. Yeah, nickel-containing compounds are green. Okay, so if you had something made of nickel and it was oxidizing, whatever, it would make a green kind of salt that would, you know, it would be obviously green, or sometimes even pale green. Okay, but it's definitely got a green tinge to it. Okay, and then we also have our cobalt-containing compounds. Cobalt-containing compounds tend to be anywhere from like a faded pink to a like bright red, right? But all cobalt-containing compounds will make pink to red solutions. Okay? The nickel-containing compounds will be green and make green solutions, and the copper-containing compounds will make blue. All right? Is this something I should definitely be on the lookout for when I'm just looking at all my unknown compounds? Yeah, if I've got a blue crystalline solid, chances are it's got copper in it. Okay, if I've got a green crystalline solid, chances are it's got nickel in it. Okay, and things like that. So that's something I would want to watch for, because again, on Tuesday you'll just have that set of unknowns, but you'll also have a list. These are their possible identities. All right, so what you're going to have to do is, by the end, say A is nickel 2 chloride, B is is copper 2 sulfate, okay, or D is table salt, or whatever. That's what you're going to have to do by the end. Everyone kind of follow what we're doing? Yeah. All right, so these colors would definitely be something we would want to remember when we're trying to figure out what's what. Okay, so the last two slides have talked about solutions that ionic compounds are in. So what does that typically say about ionic compounds and their solubility? Yeah, they're usually pretty soluble. There are a few exceptions, okay, but most common ionic compounds are highly soluble in water. Okay? Thankfully, the ones that aren't are usually ones that we don't want to have in water anyway. Things like lead, okay, stuff like that that are toxic. It's usually pretty easy to get those things out of the water supply because you just react them with something they're not soluble with. They form a precipitate and they just settle to the bottom, and you can then take the water off the top and it's clean. Okay, and that's actually what our water treatment plant does. Okay, one of the reasons that we add chlorine to drinking water is because chlorine is not soluble when it reacts with heavy metals like lead and stuff like that. So they'll form precipitates, which are powders, and they'll fall to the bottom. And then they're out of our drinking water. And so is the chlorine because it's stuck to the lead or whatever. Okay. You had a question or no? No? Okay. All right, so sorry, one thing we should add in here is that typically are usually highly soluble. We have to say usually because it doesn't apply to all of them, but they're usually more soluble than molecular compounds. Okay. Anybody need that one anymore? All right. Now, molecular compounds. Molecular compounds can be solids, liquids, or gases at room temperature because they typically have lower melting boiling points than ionic compounds do. Okay, so if you're in the lab and you see something that's one of the unknown samples is a liquid, you can automatically eliminate from the list of identities anything that is ionic. Okay, now there is going to be one unknown that's going to look like a liquid, but it's not. Okay, the issue is that we can't get this compound as a solid. It's actually ionic, but I can't get it as a solid. Okay, it's far too dangerous, and it's basically it's hydrochloric acid. We can't buy that in its solid form. It's just too volatile. It's too hard to ship, whatever. So we always get it diluted in solution already. Okay, so I'll make a note of that, and when we're going over the procedure, I'll say, okay, this material here is actually a crystalline white solid, and it's already dissolved for you. Okay.
Are we going to light things on fire to see
No.
what they are?
No, we're not doing a flame test, and that's a chemical property because it's a reaction with oxygen. So no, we're not doing a flame test. Also not advisable to do. Okay. All right. So they typically are, like we said, solids, liquids, or gases. There aren't going to be any gases. Okay. None of the unknowns in the lab will be gases. They're just really hard to keep in an open container. I don't know. Yeah, it seems odd, but yeah. So there won't be any unknowns that are gases. Okay. Other thing here, guys. So yeah, they could be. Sorry, we should underline that. They can be solids, liquids, or gases at room temperature. So like we said, if something is definitely a liquid, and there's two, okay, there's two liquids that are unknowns in your lab, then they're definitely not ionic compounds. Molecular compounds are not usually as soluble as ionic compounds. Not usually. There are some. Okay, like does sugar dissolve pretty well in water? Yeah, it does. Okay. What about alcohol? Does alcohol dissolve in water? Well, that's still dissolve. Okay. If I pour alcohol into water, I can't. They don't separate. Okay, they mix together. That means they're soluble. A liquid can dissolve in another liquid. If we just dissolve isn't really the right term to use. Okay, but if I pour a liquid that's soluble in another liquid, they just kind of gel together. Okay, and I can't see separate parts. Now, if I pour oil into water, it separates. That means it's not soluble. So if you're dealing with two liquids and you're trying to find out if they're soluble, you pour them into each other and look for any evidence of a separation. Okay, if there's any separation, it's not dissolving, it's not soluble. Okay, if you can only see one visible part, then it is soluble. Okay, so alcohol is soluble. Not that you guys would know this because you're too young, but that's why you can mix drinks with alcohol. Alcohol dissolves in other liquids. If that wasn't the case, it would float on top, which would be unpleasant. Well, it would be just like a shot with a chaser, which is, I mean, if you're into that, but you know, yeah. All right. So yeah, definitely alcohol is a molecular compound, and it does dissolve in water. Okay, liquids can dissolve in other liquids. Now, here's the thing, though. If they do dissolve, their solutions will not conduct electricity. Because when a molecular compound dissolves, it doesn't break up into positive and negatively charged ions. It stays together. Okay? It dissolves, but it stays together. So, since there's no positive and negative charges floating around, the solution won't conduct electricity. All right? So if I dissolve alcohol in water and then put a conductivity tester in there, it won't conduct. Similar thing, if I put sugar in water, distilled water, okay, that solution won't conduct electricity either. There are no ions in there to carry the current. All right. Hey, everyone okay with those so far? All right. Now, molecular compounds do not create brightly colored solutions because molecular compounds typically are not all that brightly colored typically. Right? Like sugar, even though it's a crystalline solid, is just kind of white to clear. Alcohol is clear. Okay? Like even cooking oil is not really brightly colored. It's kind of a pale yellow. Okay? They make typically clear solutions if they're soluble. Okay? Cooking oil obviously isn't soluble. Okay, acids. There's two kinds of acids, strong and weak. Okay? Strong acids are almost without exception ionic compounds. Okay? Strong acids are ionic compounds. And they're ionic compounds because they all have this acting as a metal. Okay? H plus. If something starts with H, okay, we already said then hydrogen's acting as a metal and it's an ionic compound and it's an acid. Okay? The more H plus an acid can contain, the stronger it will be. Well, partially, yes. Mostly it has to do with just acids tend to react violently with whatever they're in, right? Hydrogen is pretty highly reactive. So let's look at a couple examples here. How about this stuff? Okay, talked about this already. Hydrochloric acid. Hydrochloric acid is a very common acid. Okay, it's strong, but it's not horribly strong. And in fact, it's the acid that's in your stomach. Okay, so if you've ever had heartburn, okay, that is the hydrochloric acid in your stomach trying to dissolve your esophagus. Okay, yeah. Your stomach, inside of your stomach, there's a whole bunch of cells in the lining of your stomach that secrete mucus, and the mucus protects the inside of your stomach from the hydrochloric acid. But your esophagus doesn't have those cells. So if you get heartburn, that means that some of the acid in your stomach, it's called acid reflux, it gets past the little muscle that's supposed to close it off, and it gets into your esophagus. And you feel this sensation of burning because that's exactly what's going on. The hydrochloric acid is burning the inside of your esophagus a little bit. Okay, if you're sick and you're vomiting, okay, it's the same thing. You feel the burning as it comes up. Well, it's stomach acid. It's acidic. It's going to burn all the way up any unprotected part of your body. Okay. Typically, like very late in life, alcoholics will their teeth will just rot out because they typically get alcohol poisoning a lot and they vomit a lot, and the vomit will erode their tooth enamel, okay, and then their teeth will rot. So hydrochloric acid is a pretty strong acid. Okay, it's diluted in your stomach. Okay, it's not like super concentrated like we would have in the lab, but it's still acidic and it helps to break down your food. There are molecular acids, but most of them are weak. Okay, citric acid, for example, that's in citrus fruits, okay, is a weak molecular acid. Okay. All right, which would be stronger, this stuff or this stuff? HCl or H2SO4, which one's stronger? H2SO4, it's got more hydrogen. Okay, when it reacts, it can give up two hydrogen atoms, or hydrogen ions, sorry, two H pluses. Right, so the more hydrogen there is, typically the stronger that acid can be at equal concentrations. All right. This stuff here, guys, even hydrochloric acid, like we said, it's not the strongest acid, but it is still pretty strong. Okay, I once got put flat on my back by that stuff. I was mixing it for a lab, and I had a cold, and I was right over top of the concentrated stuff while I was diluting it, and I sneezed. And right after you sneeze, what do you typically do? Yeah, you inhale sharply. Well, I inhaled sharply all the fumes from the hydrochloric acid, and I just passed right up, fell flat down. Okay, and my colleague came into the lab, the prep room, and I'm laying there with blood coming out both nostrils, running down my face, like he thought I was dead. Okay, like you just walk into the room and you see someone laying there with blood coming out of their nose. It's not typically a good thing, right? And they're unconscious. But all that had happened was I'd inhaled it, and it kind of burned my nasal passages a little bit, enough to cause a nosebleed. Luckily, it wasn't anything too serious, and I came to pretty quickly. Okay, but it's something that you certainly have to be aware of. And the stuff we're going to be using in the lab is concentrated enough that it could give you a burn on your skin. Okay, so you want to be careful handling all of the compounds, because you don't know which one of them is hydrochloric acid. So you have to treat them all like they're hydrochloric acid in terms of lab safety. Okay. Okay. Now, what about this stuff? Would it be pretty strong? Yeah, nitric acid, very strong. Okay. And in fact, the fumes of this can actually cause chemical burns on skin. Okay. When I was in high school, we were using this. I don't remember what for, but we were using it. And some of the guys had the container open, and they were just doing stuff near the container, like, you know, moving stuff around, whatever. Their hands were near the container, and they didn't really think much of it. Well, a few hours later, they started getting big blisters and stuff all over their hands, because the fumes had gotten onto their skin, and the fumes are still the acid, okay, and had penetrated through and given them deep tissue chemical burns. Okay? Unfortunately, one of them was the setter on the volleyball team. Okay? So he couldn't play for a couple weeks, okay, because his hands were all bandaged up. So you got to be careful with this stuff. Okay, we don't use that for anything in Science 10 anyway. Okay? But yeah, but we will use the hydrochloric acid. It's pretty common. Okay, so big things here about acidic compounds. Obviously, they're going to have H plus ions in them, okay, and H will be acting as the metal. Okay, so that means listed first. Actually, you know what? I'm going to get to that in just a minute, so hold on to that. I'm going to get to it in just a minute. Okay, so the presence of H plus in a solution gives it the acidic properties. Acids are ionic compounds and share many of their properties. They're crystalline solids at room temperature, although we don't ever get them in that form. Okay, they're highly soluble in water. Okay, they dissolve very easily. You have to be careful, actually, when you are mixing the solids. If you add water to acid, it gets hot really, really fast, and it can actually break the container it's in because it can't expand fast enough. So you always add acid to water, okay, so that the water can absorb the heat. If you add water just to the acid doesn't do that. Okay. Okay. Acids taste sour or tart. Okay, good. Why would you taste it? The answer is you wouldn't. Okay. There will be no taste tests of the unknown substances. Okay. Doesn't matter. You don't know anything for sure. Right. So there will be no taste tests, okay, of any of the unknown materials. What if you need to do an odor test? Right, you waft. Okay, I see a few people doing this. You waft. Okay, so you hold the container a little ways away and you waft the smell towards you. Right, in the lab, guys, there's only two things that really have any discernible smell, and they're quite obvious. All right, so if you're going like this, you go, I think this has a smell. No, it doesn't. Okay, it's either got one and it's obvious, or it doesn't. Okay, and there's only two that are going to have any obvious odor. Okay, acids typically smell like vinegar. Okay, they have a vinegar-like smell. If you've ever smelled vinegar, it almost feels like it burns the inside of your nostrils a little bit. Well, it is actually a little bit doing that. Okay, just like the hydrochloric acid did to me, right? But they do have that kind of, that's more like the acidic smell, right? So they taste sour or tart, but we're not going to try that. And they'll turn litmus indicators to acidic colors. Typically, that means the litmus paper will turn red. We have universal litmus, which goes from 1 to 12. Okay, it doesn't go all the way to 14 for whatever reason, but goes from 1 to 12. Okay, if you dip it in there and starts turning orangish to red, okay, red definitely indicates a strong acid. And there's actually a little picture on the side of the container that tells you which color corresponds to which pH level. Okay, questions there with the acids? All right. Okay, now bases are also ionic compounds. If they're a strong base, there's weak bases, obviously, and they can be molecular compounds, but typically your strong bases are ionic compounds, and they always contain this. Hydroxide, right? Okay, so acids contain H+, bases contain OH-. All right, now, Megan, you had asked about this a minute ago. Why isn't water an acid? Here's why. From an ionic standpoint, water has the most acidic thing and the most basic thing in it. From an ionic standpoint, water's not really an ionic compound. Okay, I know hydrogen is listed first in water, but it's not water. Again, whenever water is present, it's the exception to the rule, right? And this is another one of those cases. Water is actually a molecular compound, right? It can behave ionically sometimes, but this would explain why water is neutral. Okay, from that perspective, it has the basic ion and the acidic ion in equal numbers, so they offset. Yeah, they neutralize or balance each other out. When you put water in water, okay, it's like equal amounts of H and OH are floating around. Okay, that's not really what's going on, but that's kind of how we can explain that it's neutral. Water, in fact, is a molecular compound. That's why distilled water doesn't conduct electricity. Okay. All right, so bases are ionic compounds. They'll contain OH. We talked about this stuff the other day, okay? NaOH. It's sodium hydroxide. It's an oven cleaner, okay? In its solid form, it's got like very large, like almost like saucer-shaped crystals, okay? And they're big and hard. But if you add water to it, it gets hot really quickly. Okay, it's very, very basic, has a pH of 14, which is again why it can dissolve the crud off the inside of your oven. Okay, so highly basic. And the same rules apply here. Okay, this stuff's really basic. Well, so is this stuff. Okay, it's got more hydroxide in it. The more hydroxide you can donate in a reaction, the more basic you're going to be. Okay, so they will turn indicators to a bluish color. I circle blue and red. That doesn't make sense. They will typically turn blue. Makes a little more sense. Okay, and they have hydroxide ions in them. Okay, and they'll have a pH higher than 7. I don't think I highlighted pH lower than 7 on the other one. Maybe we'll go back and do that. Okay, and they're typically going to taste bitter, but you're again not going to taste anything, okay, in the lab. But anything that does, any food that tastes kind of bitter is usually basic. Okay? That's actually one of the reasons why they tell you if you're in the wild and you're starving and you want to see if something is edible, okay, that if it's really bitter, you probably shouldn't eat it. Okay, so anything that tastes really bitter is probably not something you should eat because it's probably really basic, okay, and it might not be healthy for you to eat. Okay, on the same token, if something's like really, really acidic, it'll have that kind of taste to it, to like really, really tart, probably not all that good, like with little berries or something. Okay, you'll end up like Ralph Wiggum and right, it tastes like burning, and then you keel over. Yeah, you don't want to do that. Okay. All right, so remember here, guys, that acidic solutions have a low pH, so pH less than 7. Now again, if it's between, let's say, 4 and 7, that's a weak acid. Okay, anything that's like 2 or below is a strong acid. Okay. Okay, making sense? All right. Now I want to give you another kind of compound here and see if you can tell me which one it is, acid or base, because it's a little misleading. It's tough, isn't it? It doesn't start with H, does it? Okay, typically we said the acids, the strong ones anyway, start with H. But this is actually one of our molecular, it looks molecular, but it's actually ionic. If you look on your table of polyatomic ions, you'll see this in there. It's CH3COO, and it's got a -1 charge, and it's called acetate. Okay, so it does have H plus in it. This is acetic acid. It's vinegar. Okay, acetic acid is vinegar, and that's what it looks like from a chemical perspective. There's always exceptions to rules. That looks like it should be basic because it ends in OH, okay? And it doesn't look like it should be ionic because it starts with carbon, okay? But it is actually an ionic compound. We write these kind of ions, ones that contain organic things in them, we always write the organic part first, okay? Just one of those weird rules.
A thing you should bring into the lab for testing is HCHB11CL11.
I don't even know what that is.
Currently the strongest acid.
So we would probably not have that. Okay, so questions on that stuff there? Okay, so on Monday, we're going to be working on the design of the lab procedure. Okay, and so what I'll talk to you about kind of now and a bit on Monday are the tests that we're going to run. Okay, so we've talked about some of the properties that are going to be important for identifying our unknown compounds. Okay, so one of the first things that we're going to want to do before we do anything else in that lab is look at the substances before we do anything to them and record as many of the overtly observable properties as we can. So the first test we're going to run, we call the observable properties test. Okay. In an observable properties test, what are some things I should look at or look for when I'm looking at the materials? Color, absolutely. Color is a big one. State, yep. Solid, liquid, or gas. Are there different kinds of solids? Yeah. What if okay, we want to look at the nature of the solid or nature of the material. Okay, is it crystalline or is it soft? Okay, like butter is a solid, but I think it'd be pretty hard to argue that it's crystalline. Okay, it's not. It's soft, right? Candle wax, same thing. It's not crystalline. It's soft. Smell, yeah. Okay, and again, we want to do that by wafting, not snorting. Okay, we don't want to snort any of the unknown compounds. Most of those would not work out very well for you. Okay. By the way, if you have a cold, you should not do the odor test. Get somebody else in your group because you'll just be over everything going, and maybe you'll drip in it or something. That'd be gross. Okay, so we don't want that. Okay. Okay, Strachan, you gave me another one there. Yeah, okay. That'll actually be a separate test in addition to these ones here. But these would be our main observable, kind of overtly observable properties. The reason solubility is a separate test is, what do I have to add to the material? Water, okay? After that, I can't really check any of this other stuff, right? So I don't want to do it first. I want to look for these things first. Okay. All right, so after that, I would say, yeah, we probably want to check solubility. Now, if I add water to something and it doesn't all dissolve, does that mean it's not soluble? It just might mean I don't have enough water. Okay, I mean, given the small sample sizes you guys are going to be using in the small container you'll be using, you probably won't get everything to dissolve. So what are some other signs that it's dissolving? What are some things I can look for? Changing color of the solution. If I had blue crystals and the solution is now blue, it's obviously dissolving. Okay, a precipitate would indicate a reaction occurred though, right? So hopefully that's not going to happen. At least it didn't happen when I tested everything. Okay. I don't want to test that yet. In fact, I want to make pH my last test. Anybody know why? Exactly. For the litmus paper is a chemical reaction. Okay, when I stick the litmus paper in there, in order for the litmus to change color, a chemical reaction has to occur, which means now my material is essentially contaminated and I can't do any other tests with it. So pH is a test we're going to run, but it's the last one. Okay, so what are some other signs that the thing is soluble? In the what? Okay, change in viscosity, sure, that could be one. If I'm looking at the crystals, will they look different? They might shrink, right? Yeah, they could shrink or change shape or something like that. That would again be an indication that the material is dissolving, right? All of those are things to look for. What if there's what about temperature? Yeah, if it heats up or cools off. Yeah. Yeah, if it's exothermic or endothermic. Now, usually, again, that indicates a reaction, but for the most part, that's not too big of a worry for us. We're just adding water. Okay, but if we see a temperature change of any kind, that's also an indication that the material is soluble. Right? You will have a couple that'll get warmer, and you'll have one that gets colder. Okay, one of your unknown materials is ammonium chloride. It looks like this. Okay. Anybody ever use one of those commercial cold packs where you pop the little bubble in the middle, right? And you shake it up and it gets cold. The stuff, the powdery stuff that you can hear shaking in there is crystals of ammonium chloride. They're little, the water's in the little bag. Yeah. Yeah. The part you pop is just the water bladder that's inside. It just keeps them separate until you need them. Okay. So when you pop that, the water gets out and it starts dissolving the ammonium chloride. Ammonium chloride just looks like small little crystals, but they're shaped like a ball. Okay? They're small little kind of off-white colored ball-shaped crystals. Okay. All right, so that's solubility stuff. So in the solubility test, those are some things that we would look for, right? Temperature change. Okay, that's delta. Delta means change. If you haven't experienced that before, delta means change. So temperature change or shrinking crystals. Okay, color change of the water, okay, or would all be things that we'd be looking for in that solubility test. Okay, and we said back in the notes here that there's one test that unequivocally tells you whether it's ionic or molecular. What was it? Right. So conductivity. That's the one we should do right after solubility because it has to be in solution to do this test anyway. Okay, so conductivity. Conductivity test is pretty easy. We just have these little conductivity meters, okay? And they have a 9-volt battery that sits on the top and a little button on the side. You push the button and stick the 2 leads into the solution, and it's got a scale from 0 to 10 that tells you how good it conducts, okay? Stuff that conducts really well will read anywhere from like 7 to 10, okay? And then basically if it doesn't conduct, it's gonna read like 2 or less. Okay, there's a couple that when you put it in there and press the button, all you'll see is the little on light that indicates it's working, but this doesn't conduct electricity. Okay, our first conductivity testers didn't have that, and you couldn't tell whether it didn't conduct or whether the battery was dead. Okay, we decided that wasn't all that good, so we got ones that tell you. Okay, and then last test would be our pH test, right? Because after we test the pH, okay, we've had a chemical reaction. So those are the only tests you're going to have to run. Okay, but you're going to have 12 unknown solutions, so it takes you a little while to kind of get through all the tests. Okay, my recommendation would be is that since you're going to have them all in what's called a depression plate, okay, and a depression plate is a ceramic a ceramic plate shaped like a rectangle, okay, and it's got little pits in it. Okay, they look like that. It's got little depressions. That's why it's called a depression plate. It's not sad. Okay. It's just got little pits in it. Okay, and you'll put the samples in there and run all the tests in each one of those little pits. Okay, and then yeah, so I would say get all the materials, put them in there, and then label each depression with like A, B. We'll have markers in there. You'll be able to write right on them. Okay, label them. Do your observable properties test of all of them. Okay, then do the solubility test for all of them, and then do and so on and so on. Okay. Yes, well, because it'll be like what we talked about yesterday, right? So we'll do the pre-lab stuff on Monday where we'll talk about the hypothesis and the variables and get you guys started on writing up the procedure and making a chart for these tests. That's what we'll do Monday. Okay? And then Tuesday, you'll just be doing the lab, and it'll take pretty much the whole class. So you guys will just fill in all of your observations. Hopefully we'll get back here in time for you guys to talk over your observations, because it's a good idea when you're trying to identify the unknown substances to bounce ideas off each other. Okay, two heads are always better than one on that. Okay, so yeah, you've got group members for a reason. Talk to each other and see if people are figuring things out differently. Okay. All right. Yeah, and then after that it'll be for homework, but it'll work just like what I outlined yesterday. So. All right. Okay, a couple of things. I may have talked about this yesterday, but lab safety stuff for next week. Okay, on Tuesday you need to have proper footwear. Okay, that is that your feet have to be covered. The tops of your feet have to be covered. Okay. You have to have a hair tie if you have long hair. Okay, have a hair tie in your science binder and just tie your hair back for that day. Any loose clothing, okay, like a few of you are just kind of wearing like a loose shirt over top of a t-shirt, okay, that you'd either want to button up or just take off, okay, so that it's not, there's no possibility of leaning over and getting it in anything, okay. If you've got like a hoodie on and you got the drawstrings or something like that, you want to tuck those in or tie them up or not wear the hoodie, okay, so that the strings don't come forward and get into anything. And then the eye protection, that's the biggest one. Okay, you got to have the goggles on all the time. Okay, that's not negotiable. You don't have to wear the apron if you don't want to, but you've got to wear the goggles. Okay, if you get this stuff in your eye, it's not going to work out well for you, or the last time I had it happen for me either. Okay, because the last time I had somebody get stuff in their eye because they were wearing their goggles up here, okay, I had to take them over to the eye wash station, and they were not happy because, you know, they got something burning in their eye and they're covering their eye and screaming, okay? And when I go over to get them and try and lead them over to the eye wash station, they flail, okay? And the last time they flailed and got me right across the bridge of the nose. And I was bleeding, and then I was angry, okay? So I took a handful of hair and walked them over forcefully to the eye wash station. They're, of course, still fighting me, and it wasn't their fault. They were just panicking. So I jammed their face down into the eye wash thing. Well, there's a bar that goes across the middle of the eye wash station and then the two bulbs that stick up like this to wash your eye. So we both ended up bleeding out of the whole thing. Okay. So yeah, wear the goggles so no one ends up bleeding. Okay. Because bleeding's bad. We don't want to have that. All right. Okay. We'll call it a day there, guys. Bell's going to go here right away. So it was not.